Alrighty, good morning, A3, Precalculus CP. This is the first video that we have of Trig Equations together, alright? You know all the typical reminders by now, microphones and webcams and attendance. We've been there, done that. I am going to be grading the PAs that you submitted to me. I'm going to grade them tomorrow, so those grades should be in Aspen by the end of the day tomorrow, alright? Today is the start of Trig Equations, like I just said. Trig Equations is the last unit in pre-calc, which is like, woo! But it is also the unit that combines pretty much everything together that we've talked about. So we are going to be talking about today the unit circle. So if you have your unit circles, it would be a great time to get those out, or your exact value charts. We are going to be talking about graphs. We're going to be talking about the identities. And we're even going to talk a little bit about inverse functions, which was our very first topic all the way back in pre-calc. All right, so it kind of bridges everything together, but it's a very important topic because this is what you're going to use in calculus a lot when you're faced with something like this, the sine of x equals 1/2. What do you do? And how do you solve something that may be a little more involved than that? So that's what we're going to focus on today. All right, so a trig equation is not surprisingly an equation that has a trigonometric term in it. And you may be used to working with some trig equations already. Something like this, when you have the sine of x is equal to 1/2, we've done things like that when we've applied the sine inverse on both sides, right? If we had sine of x equals 1/2, what that's essentially asking is the sine of what is equal to 1/2. So to solve that, we would say, let's take the sine inverse on both sides, just like that. And what the sine inverse of 1/2, I would use my handy dandy calculator, and I'd say the sine inverse of 1/2 is 30 degrees, or in radians, I'll write that as pi over 6. Okay, which again is 30 degrees. Because the sine of 30 degrees, the sine of pi over 6, is 1/2. So that's why if you have the sine of x equals 1/2, you're like, what value, the sine of what value is equal to 1/2? It's 30 degrees, or pi over 6. But, does that make sense? So hopefully that makes sense. But what's weird is the fact that that's not the only value for which the sine is 1/2. Take a look at our handy dandy unit circle. Oh yeah, you never thought it'd be back. Well, the unit circle, if you take a look, the sine of 30 degrees is 1/2, absolutely. But the sine of 150 degrees is also 1/2. Do you notice that? The sine of 5 pi over 6. So wouldn't I have to say that for this problem, well, my answer is pi over 6 or 5 pi over 6. Right? Because the sine of 5 pi over 6 is 1/2, so who's to say that x is not equal to 5 pi over 6? But wait a minute, couldn't I also then just go around the whole unit circle again and say, well, what about 30 degrees plus 360? Remember how we talked about taking whole rotations around the unit circle, and you still end up with something that has the same cosine and sine values? What about, what is it going to be, 390 degrees, right? Which is going to be written as 13 pi over 6. Right? That's 390 degrees. Okay? Wouldn't that also have a sine value of 1/2? So shouldn't that also be included in our answers? And what about if I go even from there to here? That's going to be 17 pi over 6. That's just 5 pi over 6 plus 12 pi over 6, or plus 2 pi. That would be, how many degrees is that? 150 plus 360 is what? 5, 10, I believe, if I'm doing my mental math right. What would that be? Well, how is that also a solution? How many solutions are there? Wouldn't this just keep going on and on and on forever and ever and ever? And the answer to that is, well, kind of. But we have to understand how the restrictions on the inverse sine function works in order for us to be able to answer this question accurately. Because, yes, technically, if you're talking about every single angle that could possibly exist in the world, then yes, the sine of x equals 1/2 would have an infinite number of solutions, right? What if you went in the negative direction, right? You went this way, and you said, or this way, and you said, well, instead of pi over 6, you could say it's negative 11 pi over 6, right? Or negative 330 degrees. That would also have a sine value of 1/2, all right? The way that that's written in sort of fancy math terms is you could say that x is pi over 6 plus 2 pi n, where n is an integer. Like saying n is 0 means that you've made 0 revolutions around the circle, so it's pi over 6. If n is 1, then you would do pi over 6 plus 2 pi, meaning you made 1 revolution around the circle, arrived right back at that same spot as pi over 6, and that would have the same sign value. If n is 2, same deal, right? Or x is 5 pi over 6 plus 2 pi n. And again, we're saying that n is an integer. And that's the way it would be written in a very fancy math way. That means that n is an integer. Okay? So that's how it would be written mathematically. And that would be actually your solution if we were looking for every single angle that existed in the world. But why then does our calculator tell us 30? Why does our calculator tell us it's pi over 6 plus 2 pi n? Why does it even acknowledge the 5 pi over 6? What's going on with that? What's going on with that? Well, that all relates to how the graphs for these things actually look and how they actually behave. I think that this is important background info for you, so I'm going to now present to you the graphs of these functions and show those off for you. All right, we're going to switch layouts here. We are going to switch over to my computer science layout. Look, we got a screen within a screen within a screen within a screen. Pretty cool. But just so I can show you the graphs. Okay, it's not AP Comp Sci all of a sudden. All right, notice that this graph right here represents the sine of x equaling 1/2. Right, sine of x equals 1/2 at pi over 6. This red thing is the sine. The blue thing is 1/2. They're equal where they intersect. So it equals pi over 6, 5 pi over 6. This is what we said. 13 pi over 6, 17 pi over 6, 25 pi over 6, 29 pi over 6. Like, you can just keep going forever and ever and ever and ever and get infinitely many solutions. Okay? On the equations, or a lot of the equations that we work with, we are going to be restricting it to just look at this first rotation. So if you're solving an equation and it says that only consider x values from 0 to 2 pi, well, then that would have two very distinct solutions of pi over 6 and 5 pi over 6. Okay? However, there is even another however. This function really doesn't have an inverse, right? Do you remember, this may be going way back, but for a function to have an inverse, it has to pass the horizontal line test. For something to be a function, it has to pass the vertical line test. But for a function to have an inverse, it has to pass the horizontal line test, right? If you notice, if I just swapped x and y, that's how you create something to be now an inverse, this would not pass the vertical line test because now you could draw a vertical line and it would intersect all those functions. And that would be very bad, right? Oh, I want to change that to y, right? That would not be a function. If you draw a vertical line, you go through more than once, not a function. So what we essentially have to do, or what we're really tasked with, is figuring out, go back to our normal, figure out how we can restrict the function of sine such that when we invert it, we can preserve the fact that it's still a function and also hit every possible sine value. And that's where our unit circle comes in. So go back to here. Let's go back to unit circle. Back to our good pal, the unit circle. Okay? Well, our good pal, the unit circle, really tells us everything that we need to know about sine. And I wanted to do this in, there it is. I want to do this in pencil because I need to erase it for my A4 class. So let me ask you this. When we're dealing with sine, what is the, sine, remember, measures the vertical distance, right? What is the largest sine value that you can get? The sine of what on the unit circle is the biggest you can get? That's 1. What is the smallest sine value you can get? that's negative 1. So do you see that if I only consider this portion of the unit circle from here to here, let's talk from here to here, I can hit every possible sine value between negative 1 and 1, right? Here, if I go down this way, it really just hits all of those sine or y values again, right? Like 1/2 having that be, or sorry, 1/2 right here, having that be the sine value is already accounted for over here, right? This is just redundant. If I just look at this half of the unit circle, consider from bottom to top, that allows me to capture every possible sine value between negative 1 and 1. Okay? So what I would like to say is I'd like to say that the inverse of sine, go back to the graph, I'm going to switch a lot this class, going back to the graph, I would like to say that, oh, not that, I would like to say the inverse of sine can be restricted from, watch this, 3 pi over 2 to pi over 2. But that doesn't really make any sense because 3 pi over 2 is bigger than pi over 2, right? So another way that that can be represented, 3 pi over 2, think of if you subtracted 2 pi, it can be represented as negative pi over 2. Negative pi over 2. And if I now apply that as the inverse function, that is the inverse function of sine, okay? And so when your calculator, specifically, we're talking about sort of why your calculator spits out just the answer of 30 and why didn't it say anything else. When your calculator calculates the inverse sine, it only considers those values from negative pi over 2 to positive pi over 2. Meaning, it's only going to consider the first quadrant and the fourth quadrant. Okay? Because just those two quadrants give us all of the information that we need for the sine function. Okie doke. I know that's kind of a weird idea, but think about it. With just those two quadrants, first and fourth, think of that the right half of the unit circle. Get my lefts and rights mixed up. The right half of the unit circle gives us all the possible sine values that we could possibly hit. So does the left half of the circle, but it's more efficient for us to balance around 0. Like, why have our function shifted over? Might as well go around 0. And so the sine inverse is restricted from negative pi over 2 to pi over 2. Okay? I'll give you a little bit more notes on this in a minute, just talking about it for now. Cosine is very similar, right? If I look at when the cosine is 1/2, notice that cosine of pi over 3 is 1/2, cosine of 5 pi over 3 is 1/2, and also 7 pi over 3, and also 11 pi over 3, and also forever and ever and ever and ever, right? Because you can just keep going around that circle. But going back to my unit circle, we're going to be flipping back and forth a lot. Back to my unit circle, right? What part of this unit circle gives us all of the cosine values? Remember that cosine is x. Do you agree that if I just look at the top half of the unit circle, it gives me all of the cosine values that I need, all the way from negative 1, getting bigger, getting bigger, getting bigger, getting bigger, now 0, getting bigger, getting bigger, getting bigger, now 1. You see that? That top half, quadrants 1 and 2 of the unit circle, really give you every possible cosine value that you need. Those cosine values are then just repeated down here. So, going back to the graph, we can restrict, where'd the graph go? There it is. Going back, I was like, where'd my graph go? Going back to the graph, in order to find the inverse function of cosine, we can restrict from 0 to pi. If you notice, it looks like this. Notice how that touches on every single cosine value. After that, it would only continue to loop back up and cross over, therefore failing the horizontal line test. And so to find the inverse of that, I would switch x and y, and it would look like that. That's what the inverse function of cosine looks like. It goes from 0 to pi. In other words, It just talks about the first two quadrants of the unit circle. That's why if you did something like cosine inverse of 1/2, I'll do it for you on a calculator. Right? Do you notice that cosine inverse of 1/2 on the calculator, see it up there, it gives you the answer of 60 degrees. But why doesn't it give you 300 degrees? 300 degrees also has the cosine value of 1/2. Why doesn't it consider that? Because the answer is because the cosine inverse function only focuses on quadrants 1 and 2, because it's able to get all of the cosine values just from that top half of the unit circle. Alrighty. Tangent works just like sine. Tangent, we didn't really take a look at the graph of the tangent. The graph of the tangent is very weird. It has a lot of asymptotes because tangent has undefined points, because tangent is talking about slope. Think of the fact that if you considered just looking at one revolution of the unit circle from 0 to 2 pi, it still definitely fails the horizontal line test. So to encompass all of those possible slopes of lines that you could possibly get, tangent is also restricted from negative pi over 2 to pi over 2. Because if we're looking at slopes of lines, that gives us everything from straight down all the way around the circle to sideways, all the way around the circle to straight up. I can't bend my arm that way, but that's how it works. Okay? So tangent is also restricted from negative pi over 2 to pi over 2. Okay? If I look at that, notice that that now passes the horizontal line test. That gives me everything I need. And if I take the inverse looks like that. Okay? Which is a function. All right? So that's sort of the connection to the graph. We need to restrict these domains such that it may seem like unnecessary and like, why are we doing all this? We need to restrict the domains such that the functions are invertible, because you can't be invertible if you fail the horizontal line test. So that's why we're only talking about specific pieces of the function, and that's why your calculator only considers specific pieces of the function, because otherwise it would be confused. It would say, well, how am I supposed to know? If I have sine inverse of 1/2, am I talking about 30 degrees or am I talking about 150 degrees? I don't know. So your calculator does exactly what we just did, and it says, let's just limit sine to look at the right half of the unit circle. So we can get all the possible sine values in there, and the one that happens to be 1/2 is 30 degrees. It is going to be your task when we move into trig equations, actually solving real deal equations, to recognize the fact that, oh, if we're going from 0 to 360, that also would include your 150 degrees. Okay? But that's why your calculator only tells you 30. Alrighty? So, in short, let's get out of this. Oh boy, I want to. No, I don't need your help, Chrome. Get out of here. In short, right here. Go back to here. Let me give you some actual notes on this. Okay? Here's our fun unit circle. Get out of here. All right. In short, we have this function of y equals the sine inverse of x. Okay? If I am taking the sine inverse, right, the domain of that function is from -1 to 1. Because the lowest the sine value can go on the unit circle is -1, and the highest it can go is +1, right? So your domain of the sine inverse function is from -1 to 1. You can't take the sine inverse of 3, right? No angle has a sine value of 3, so that wouldn't make any sense, okay? Your range, the actual answers it's going to give you, is from -pi/2 to +pi/2. This is how your calculator works. You're going to get an answer from -pi/2 to +pi/2. And the graph looks pretty much like we just saw. I'm going to try to draw as accurate a picture as possible. It goes down to -pi/2, up to +pi/2. The sine of -1 is pi/2. The sine of 1 is pi/2. So it looks like this. Or sine of pi/2 is 1, rather. And it looks kind of like that. Okay? Another word that is often used to talk about these inverse functions, and a word that I'm going to use going forward, is this is commonly referred to as the arc sine of x. Okay? The reason being, this is used a lot in calculus. And the reason being is so that it doesn't get confused with exponents. When we do this little -1, sometimes that can be mistaken for an exponent. In calculus, you'll see it much more referred to as the arc sine. It's the same thing, just a different terminology. It's called arc sine. All right. We also have our cosine one. It's called the arc cosine. Arc sine, arc cosine, and not surprisingly, arc tan. Your domain of that is also from -1 to 1 because your lowest cosine value you could possibly have is -1. The biggest one is +1. Your calculator will give you an answer between 0 and pi when you do that. And it's actually defined for 0 to pi in the range. And the graph for that looks like this. It goes from 0 to pi. And the cosine of pi is -1. The cosine of 0 is 1. And then right in the middle here, it should be pi over 2 because the cosine of pi over 2 is 0. And it would look kind of like this. Okay? And last but most certainly not least, if I have tangent, could write that again as arctan. Your domain is all real numbers. You could take the tangent of anything, the tan inverse of anything, because that's just going to have a slope. Tangent talks about slope. It's like, what's going to be the slope of that line on the unit circle? And the range of that goes from -pi over 2 to +pi over 2, just like sine. It just looks at that quadrant 1 and quadrant 4 of the unit circle. The graph of that looks like this. I have pi over 2 up here. I have -pi over 2 down here. I have 0, 0, and we go kind of like this. Approaching but not touching that. Approaching but not touching that. Okay? So, what all this means. So you might be like, well, what does all that mean? Why bother? Well, that tells you why the calculator only gives you certain responses and why only technically the sine inverse of x is 30. Why is it technically not 5 pi over 6? If it were 5 pi over 6, then your function would not be invertible because it would fail the horizontal line test. Your task when we deal with equations is going to be to recognize that if we're talking about the whole unit circle, yes, your calculator will only tell you it's 30 degrees, but you have to understand that it is also including 150 degrees. Even though your calculator doesn't tell you that, even though the graph doesn't tell you that. That's what you have to understand. So that's sort of the takeaway. So taking a look at some concrete examples here. Do them right in this little area down here. If I actually had the sine inverse of -1, right? What I would do is I would look at, you know what, I should probably note that we're looking at these specific quadrants. Sine looks at quadrant 1 and quadrant 4, 1 and 4. Cosine, we look at quadrant 1 and quadrant 2. And tangent, we look at quadrant 1 and quadrant 4. Okay? So if I have the sine inverse of -1, what I would do, since sine is on quadrant 1 and quadrant 4 is where your calculator looks, I would look to see quadrant 4 and quadrant 1. Where do I find a sine value of -1 in this portion of the unit circle? Right here. I don't call it 3 pi over 2 though. In terms of sine, it's defined as -pi over 2 to pi over 2. That's -pi over 2 to pi over 2. So I would say that my sine inverse of -1 is -pi over 2. Okay? I would say that. And again, remember, negative radians just means that you're going this way around the circle as opposed to going this way around the circle, right? If I have this is -30 degrees, this is -45, this is -60, that's -90. -pi over 6, -pi over 4, -pi over 3, -pi over 2. Okay, and the positives. Let's do another one. How about if I have the cosine inverse of rad 3 over 2, of negative rad 3 over 2. Okay, let's do that. Cosine inverse of negative rad 3 over 2. Again, I'd look at my handy-dandy unit circle, and I'd say, well, just looking at the top two quadrants, because that's where cosine is defined, that's where the inverse of cosine is. Notice from 0 to pi, the inverse of cosine in the top two quadrants. Where do I see a cosine value of negative 3 pi over 2? Right there. And so your calculator will give you the answer of 5 pi over 6. Okay? And so, and the true answer of what is the cosine inverse of negative rad 3 over 2, it is 5 pi over 6. Even though that also has the same cosine value, right? It just, it doesn't fall within the invertible range. So you would just have to make that connection. Your calculator, and mathematically, that connection doesn't exist. Okay? That's a connection that you make to say, ooh, I know this fact. Okay? Lastly, or maybe a couple more. If I have the tangent inverse of 1. Tangent is defined just like sine. Tangent and sine are quadrants 1 and 4, because that's enough information to get every possible tangent value. I would look at quadrants 1 and 4. Where do I see the tangent of value of 1? Well, a tangent value of 1, remember, is sine over cosine, is tangent. We're looking to see when are we doing the same number divided by the same number. It's right here. Do you see that? And so I would say that that's pi over 4. Okay? When I truly do sine inverse, I'm looking at, again, quadrant 1 and quadrant 4. Cosine inverse is quadrant 1 and quadrant 2. Tangent inverse, quadrant 1, quadrant 4. All right? Even just doing a couple easier ones. How about the sine inverse of 1/2? Well, the sine inverse of 1/2, since it's sine and it's inverse, the arc sine, I'm going to look at quadrants 1 and 4. Where do I see that value of 1/2? Right here. It's 30 degrees. That's what we did right up there. Pi over 6. Okay. Looking here, let's just use the other terminology. If I say the arc cosine of, let's say, about negative rad 2 over 2. Cosine inverse, I'm just looking from 0 to pi. I'm just looking in the first two quadrants. Where do I see that negative rad 2 over 2? Right there. So your calculator is going to spit out 135 degrees, or 3 pi over 4. Okay? And last but not least, we can say, well, what about if I did something like the tangent? Let's do arctan, just to use that notation, of negative 1. Tangent inverse only looks in quadrants 1 and 4. So I'd look here. I'd say, ooh, let's look at quadrant 4 and quadrant 1. When do I see that the tangent value would be negative 1? It would be down here, I'm pretty sure, right? Because I would be doing this divided by this, or this divided by this, that's going to be negative 1. That is not 7 pi over 4, but now negative pi over 4. Because we go from negative pi over 2 to pi over 2. Negative pi over 2 to pi over 2. And that all has to do with the graph as to why we do that. And so you would recognize that it's that. Okay? Again, sort of the point of this little introduction in connection to the graphs. I know it's complicated. I tried to trim it down as much as I could for you, because you could really talk about this for like a week. Tried to trim it down as much as I could for you. The point of this is to recognize the answers that the calculator is going to provide you. If I said arctan of negative 1 in the calculator, yes, it is true that in the unit circle, 3 pi over 4 has a tangent value of negative 1, as does 7 pi over 4, as does, just keep going, 2 pi, 2 pi, 2 pi around, but as does all those infinite number of angles. But your calculator is going to give you that one. Okay. So it's a matter of being able to interpret the results that you get on your calculator. And sometimes it might not even be a nice, pretty one, right? you'd have to interpret the fact that you get a negative angle as, okay, that's actually a fourth quadrant angle, and it could actually match up with a second quadrant angle. It's just talking about why does your calculator tell you these particular things. That is particularly important in calculus as you go forward. All right, so that's why when in my calculator, if I do the tangent inverse of, let's see, -1, notice I get negative 45 degrees. It doesn't say, oh, you can't see it because of the glare. Negative 45 degrees. It doesn't say negative 45 degrees and 135 degrees and 315 degrees. It only goes from negative pi over 2 or negative 90 to positive 90. Because that's the invertible region. Whew. Hopefully all that stuff made sense. I am going to post some supplementary notes just in case it didn't. I know that's a pretty complicated idea. Like I said, I tried to squish it into a half hour and tried to strip it down as much as I could for you to really make it make sense. But this is why your calculator gives you the answers it gives you. It all has to do with the graphs of the inverse functions and how they're defined. Alrighty? Whew. There is some practice work on Classroom that I would like you to do to try to find the inverse values of those particular things that are there. It will be due on Friday. It's not graded, but try to do the best you can. It's only to your benefit. I'll have the answer key created and posted tomorrow. That's what I plan on doing in addition to grading your assessments. Thank you for staying for a couple extra minutes. I really appreciate that. I hope you have a fantastic rest of your day. I hope that made sense. I will post some supplementary notes to try to clarify it even more. And I'll post the answer key, which should hopefully even clarify it more. But you have the handy dandy calculator, you have your handy dandy notes, so you should be in good shape. All right. Thank you again for everything. I hope you have a great day, and I will see you on Friday. Bye, everyone.
Have a nice day.
See you later.
Have a good day.
See ya.